Okay, so this is the second part of our introduction to the x86 architecture. We are going to talk about the control instructions. So in the slides, you can see there is a YouTube video. And take a look. It's very interesting. So let's go to the slides here. So we have talked about um, the registers. So here, there are the 16 general purpose registers for 64-bit architecture. Right? For the 32-bit, there are 8 registers. So you need to remember our modern computer, right? Modern x86 processor, they support both 64-bit operation and 32-bit operation. So there is a controlling bit to control which mode to execute the code. Okay. So in addition to those registers, there is another register in the x86. It's called a 64-bit. It's called R flags. In the 32-bit architecture, it's called E flags. It contains a lot of, as a name, has a lot of flags like CF, CF, SF, OF, and there are many others. So whenever you execute an instruction, it will implicitly set those control flags in the E flags register or R flags register. And then you can use some instruction to test for those conditions and do the conditional branching, like jump, right? Jump if it's less than or equal. So there are a number of such instructions. So every time when you execute an arithmetic instruction, you're going to set those 4 flags. Like CF, it's called a carry flag. ZF, it's called a 0 flag. SF, it's called a sign flag. These are used to for the signed operand. Then there is a overflow flag. This is also used for the sign flag, signed operands. So those are the conditions when those arithmetic operations will set those flags. If it's CF, if there is a carry out or borrow from the most significant bit. So this indicates the unsigned overflow. So the ZF is simple. If the result is 0, ZF is set. The SF is also simple. So if for a signed number, signed operand, if t is less than 0, then the SF will be set. So as we know, in the computer, the numbers are represented as a choose complete. So if the highest bit of the result is 1, then SF will be set. So the OF is more complete. Okay? If the choose complement overflows, so if A larger than 0, B larger than 0, and T less than 0, right? If A less than 0, B less than 0, but T is larger than 0. So we have an overflow here. Again, those flags are not set by the LEAQ instruction. So as we have mentioned before, we can use LEA instruction to do 2 things. The first is calculate addresses, right? The second, it can be used to encode some simple arithmetics. Okay. So here is the condition for each individual flag, ZF. If the T is 0, SF here. If the highest bit is 0, which means this is a negative number because numbers are represented in 2's complement inside the processor. So if the highest bit is 1, it means that it's a negative number. The CF is that when we have a carry or a borrow, when you do a carry, there is addition. Okay, so we have two very large numbers. Then there will be a carry to the higher number. This number will be discarded, but the CF bit will be set. Okay, so this is the similar for the borrow. These are for the unsigned arithmetics. Okay, this reported the overflow. The OF is decided by those conditions. Okay, for the signed arithmetic, those reported the overflow. O means overflow, right? So those are the 4 conditions for arithmetics. So there are a number of other conditions which are not affected by the arithmetic operations. So conditional code, they can be explicitly set, right? We have mentioned that if you execute an instruction like add, right, or subtraction, so you are going to implicitly set those condition code. But you can also explicitly set those conditional code. So there are 2 instructions. One is the compare instruction. So if we have compare like B and A, it's like computing A minus B without setting the destination. Normally, if we do a subtraction, right? Subtraction B and A, it will actually calculate the A minus B, then save this in the operand A. But now, with the compare instruction, there is no setting part. So it only calculated the A minus B and setting those flags. Okay, so that's the difference between subtraction and the compare, right? So the subtraction will change the destination register, but for the compare, it will not change the destination register, right? So this will be the condition to be set. So there is another instruction. It's called a test instruction. So the test instruction is like calculate A and B, right? Bitwise and set those 2 flags, 0F and SF. So again, SF is set when the highest bit is 1, right? So now ZF is set when both numbers are 0. Okay, so we often use this to, as a fast way to test whether IX is equal to 0 or not, right? Because when you AND itself, it's like IAX and RAX, it equals to RAX. So now ZF will be set if RAX is 0, and the SF will be set if RAX is less than 0. So this is often used in the code generated by the compiler. So you know so when Intel designed their instruction set, right, they have a intended purpose for instruction, but often the compiler can use whatever they want, right? So this including using this kind of which looks to be a very kind of weird usage, okay? But they are normally faster than the normal way to do, say, test whether IAX is 0, right? Okay, so there is also a set instruction. So the set instruction is very interesting. It will set the lower byte or the byte of a destination to either 0 or 1 based on the condition. We can look at an example here, like set S. Let's look at this here. So if we execute the instruction like set S, like E, like AL, right? So it will set AL to either 0 or 1 depend on the SF flag. Okay, as we have mentioned for the say EAX register, right? So there is a 32-bit. So it will actually set only the lowest bit. It's either 0 or 1 here, but all those other bits will keep its current value. It will not change the other higher and higher higher order byte, right? So this will be the byte 3, byte 2, byte 1, byte 0. It will only change the byte 0. Okay, so it will not change byte 2, byte 3, byte 1, or those higher order bytes. So there is another instruction which could be very useful for the move ZBL. So this is something called a 0 extension. Zero extension move with 0 extension. So it basically will set the higher 32 bit to 0. It will set the upper 32 bits to 0. Right? We can look at an example here. So this simple function will return whether x is larger than y. Right? So as we have mentioned, x is passed in the RDI register, and the y passed in the ISI register. When this function is converted to assembly code, it will first execute the compare instruction. Okay, so RDI will be x and ISI will be y. So basically, it will calculate x subtract y and set the flags. So if it's greater than 0, it means x is greater than y, right? So it will set the AL to be 1. Okay? So let's look at this will be EAX register. we know all the return values are saved in the EAX register, right? So we have all those bytes here. So it will set the EAX to be 1, assume X is larger than Y, right? But all those higher bytes, it could be anything in there. Like this could be FE, this could be EF, this could be 0. So if you just return this, right, this will give you a wrong result, especially if the X is less than or equal to Y. In that case, the lowest bit will be 0, right? Lowest byte will be 0. So to solve this problem, what you want to do is to call the move ZBL instruction. So you move AL to EAX with 0 extension. So basically, AL is 8 bits, right? EAX is 32 bits. So what this instruction does is copy the 8 bits of AL to the EAX register. Okay, so it will be either 0 or Y, depending on this condition here. And it was then, because AL is only 8 bits and the EAX is 32 bits, it will set the other bits in the EAX register to be 0. So this is called a 0 extension. So because the source register or source operand is only 8 bits, but you need to move 32 bits into the destination register. So now what this instruction does is to copy over the lower bits from the source register and 0 extend to the higher end bits. Okay, so this instruction is very useful in the compiler. Okay, so we have covered this. The conditional branches. So we have talked about conditional code. So let's talk about the conditional branches. The Intel instruction set provide 2 ways to do the jumping. Okay, so there is a relative jump. So basically, we know when we execute the program, right, there is a EIP or RIP, depends on which mode you are running. It points to the next instruction, right? Next instruction to be executed. So the relative jump is basically say jump plus and minus offset. So to calculate the destination address, it's basically EIP plus and minus offset. Okay, so this is hard coded in the program, right? So you have a number of instructions. So when you do the jump, say, okay, so add say 8 bytes to the EIP. So if you look at this kind of instruction is hard coded. In your program, right? So the attacker cannot change that. So this is called a relative jump. There is another jump. So it can jump indirectly to, for example, a register. So what the processor does is to load the EAX to the EIP register. Okay, so if you look at this kind of jump, right? So this can be this can also be the call instruction, right? So you can use this kind of instruction to implement a function pointer. Say you have a function pointer, you assign to this, say, a compare function, right? Then you can call this function using the function pointer. Right? If we look at this kind of usage in the C programming language, you are going to say move, right, the CMP into the EAX register, right? Then you can call EAX. Of course, you need to load the parameters in between. So now, with this kind of structure, so the destination is in a register, right? If somehow the attacker can override this register, if the attacker can override this register, then it can control the control flow. It can take over the EIP. So in this case, we think there is a control flow hijacking. When we talk about the, say, buffer overflow attacks, so one of the main purpose is to hijack the control flow. Right? Then it can execute anything under the control of the attacker. Okay, so those are called indirect jump. Indirect jump or indirect call. Of course, there is also relative call, right? So the relative call will be a call instruction, but the offset is hard coded, just like the relative jump. Okay, so if we look at those instructions, those are all relative jump instructions. Okay, but there is some of that can also be encoded with the indirect jump, right? So you can also have a indirect jump, like say register. But normally, those others are used for relative jump. So there's a jump instruction with some conditions, like GE, right? So this jump will only jump if ZF flag is set. It means it's equal to 0, right? So let's look at another example, like GNE. If it's not equal or not 0, then it will test for condition of not ZF. Okay, this will be the jump instructions. Here we can look at an example here. So we can have a function which will return the absolute difference, right? It means it will always return the positive number. Okay, so as we mentioned before, RDI X is in the RDI register, Y is in the RDI register. It's in the RSI register. So the first instruction will compare the RSI and RDI. So it will basically calculate the x minus y. If it's LE less than or equal, okay, if x is less than or equal y, it will jump to this location, L4. So the L4 is called enable, right? So normally in assembly code, you assign the label to some location in your assembly code. Then you can use the jump instruction to jump to this label. So the assembler will automatically convert this label into a offset, right? Because you don't want to calculate, say, how many bytes is a move queue, how many bytes is a subtract queue, right? And also the return instruction. You don't want to manually calculate how many bytes those are, because the compiler, the assembler can do this for you. So normally you just assign a label to your code, and you can jump to your label. Okay. So if it's x is less than y, then we need to calculate the y minus x. Right. So the y is in the RSI. So we move RSI to RAX, then we subtract RDI. This will be x, this will be y from RAX, and also save the result to RAX. Again, the return value are always returned in the EAX or RAX register. It depends on which mode you are running in. Okay. So if the jump instruction found the condition to be false, it will execute this branch. So in this branch, it will calculate x subtracted by y and save this to the RAX register. Okay. So when we look at this kind of a function on the left side, we can often translate it into a equivalent code in the right side. So we don't need to use the assembly instructions to express the translation, to illustrate the translation. This will be very obvious when we talk about the loop instructions. So here is another example. This will be the C territory conditions. So we have a test, then there is a then expression and a else expression. So when the compiler generates the code for this expression, it's going to first to do the test, right? If it's not test, let's go to the else branch. Otherwise, let's take the then express. Okay, it's pretty simple. So another interesting instruction would be the conditional move, right? So we have talked about like a set, for example, set S instruction. This will be the conditional set instruction. It will set the lower byte of the operand according to the condition. So the conditional move are actually very similar to a conditional set. You can move to a destination register according to some condition, right? So if the condition is set, if the condition is satisfied, the the data will be moved to the destination register. Otherwise, it will not move to the destination register. So here we can show an example here. Still the same test, then expression, and the else expression. To convert this into a conditional move, we can first calculate the then expression, then the else expression. Then we can do the test. Then this will be encoded with a conditional move instruction, right? So then normally we initialize the result to be then expression. Then we tested the condition. If the condition isn't satisfied, so we can assign the else expression to the result. Then we can return the result. So here is an example. So if x larger than y, so the result equal to x minus y. So if the otherwise, the result equals to y minus x. So here we can take a look to encode this into a conditional move. So this will be the conditional move. So all the conditional move instruction begins with cmove prefix, then add with a condition, right? So the cmove, it means this is a conditional move. Then this will be the condition. So it's very similar to the jump instruction, like jump LE, right? Less than or equal. So if you look at this, right? So we first calculate y, x minus y. So the result it will be in the RAX. Then we calculate the y minus x, the result in the RDX. Then we compare x and y. If x is less than y, we're going to conditionally move. We will conditionally move RDX into RAX. So this will only happen if x is less than or equal to y. Then RAX equals to y minus x. If this isn't true, this will not happen, then RAX equal to x minus y. So if you look at this, right, so to convert this piece of code into conditional move, we actually always calculate those two values. Right, make sense? Because we want to avoid a branch, conditional branch. So in the computer architecture course, you know, conditional branch is a branch hazard. Right? It will introduce performance overhead. So if those calculations are simple, it will actually improve the performance. But in some case, conditional move could be bad for the performance, right? For example, if you have you need to calculate two expensive computations, right? So this will introduce performance overhead, right? Because both value will be computed, and one of them is unnecessary. Okay, so it only makes sense when the computations are very simple. There is also a risky computation. Here is an example, right? So we test whether a point is near or not. If it's not nil, we're going to get its value. Okay, we dereference the pointer. Otherwise, we return 0. But if those both values are get computed, what will happen if the p is 0, right? Or p is nil? In that case, we are dereference the memory of 0. That's called a nil pointer dereference. So this is actually a security vulnerability. This is especially harmful in a few years ago, but now things is much better. Okay, so we're not going to talk about this in details. Right, so there's also computation with side effects, right? Okay, so this will cause unsafe or illegal computation. So the conditional move are not used, are not always used, right? So those three conditions or those three situations, we cannot use conditional move. Okay, next we're going to briefly look at how the loops are being converted by the compiler. So to understand how those loops are being converted by the compiler is actually very useful in the reverse engineering. Right? In the reverse engineering, you are given the binary code. You try to make sense of the structure of the original program. Right? So you can, in some case, you can use a reverse compiler or decompiler to convert the binary into the C source code. Right? Normally, they need to understand the how the compiler does things, especially for those loops. So here we just look at some simple examples. So this one will be the do while loop, right? So here is a do while loop here. Okay, so the do while loop, you will always execute the loop body at least once. Then at the end of the loop body, you are going to test for the condition. So here is how this is being converted into a go-to version, right? So you can set a label here called loop. Then this will be the loop body. So at the end of the loop body, you test for the condition. If it's true, you will go back to the loop. Okay, so this is how the do and while being converted into a go-to structure. So if you have this structure, right, so that it's pretty easy to convert this into a assembly. Here is the general do while translation. You do the while, those are the keywords. Then we have the body of the do while loop and the condition here. So to convert this, we set a flag, a label to mark the whole structure. Then there is a body. At the end of the body or after the body, we test for the condition. If it's true, we will go back to the loop. Okay. So here is another example for the while sentence. So the difference between do while and the while is that do while will always execute the body of the loop at least once. But the while, it may or may not execute the body according decided by the test condition. So this is translated into at the beginning we have a go to test. So here is neighbor test, right? So it will first go to the conditional test. It will first go into conditional test. And if the test is satisfied, it's going to go back to the loop. Okay. Otherwise, it's going to exit the loop. This is how the while loop is being translated. So let's look at the one last example. So the for loop, right? In the for loop, for C is actually quite complicated. So there is an initial sentence or initial statement. It will set the initial condition. Then there is a test condition. This will be the condition to test. Then there is update, right? How to update the say some loop variables. Then we have the body. So we can say like for, we have an example here for I equal to 0. If I is less than say 10, let's do I plus plus, right? This will be a very simple for loop. It will run the body 10 times. And to convert this into the into the while version, it will first convert into the while version. We have a init, right? And this will be the I equal to 0. We first execute this before entering the while loop. Then we do the while of condition. The init will be I equal to 0. The test will be I less than 10. Then we have the body. After body, we have update. Right? Now we can use this part to convert the while loop. Right? So let's just do that. So we have an init here, right? Then we have a loop. Then there will be a body and update. So now we have a test, right? If test, let's go to loop. This will be done or under loop. So here we need to do the go to test, right? So this is how we can translate the for loop into the go to format. So we first do the initialization. Then we go to the test, right? So at the test, if the test condition is true, we go to loop. Okay. So after executing the body of the loop, we're going to do the update. Okay, those are the part of conditional code or conditional branch you need to understand for this course.